Question 4 of Paper 1, the year 2002, is about systematic and random uncertainties. This question tests whether you can be able to identify a systematic uncertainty or a random uncertainty, or identify where such situations have been described. So let's go straight to the question. In the question, we are told that a student measures the time t for a ball to fall from rest through a vertical distance h. Knowing that the equation h is equals to a half gt squared applies, the student plots the graph shown. And here we have the graph. Which of the following is an explanation of the intercept of the t-axis? First of all, let's look at this equation. The equation h is equals to a half gt squared. There are two variables here. T is the independent variable while h is the dependent variable. So plotting a graph of h against t squared will give us a straight line through the origin, because h would be on the y-axis, t squared will be on the x-axis, and of course we have the gradient, which would be g over 2. That means that this gradient m will be a half g. So we can as well as plot a graph of h against t squared, and we'll still get a straight line through the origin. That is why part D or option D is wrong. The student should have plotted h against t squared. Plotting h against t squared would not have changed the nature of this graph. It would simply be a straight line through the origin. Now let's take square root to both sides. If we take the square root to both sides, we are going to get the square root of h is going to be the square root of a half g, that is the square root of g over 2, and then t. Again, here we can plot the square root of h on the y-axis, t on the x-axis, and m will be the gradient. So in this case, the gradient will be the square root of a half g, or the square root of g over 2. So this graph is correct according to this equation. We have already stated that this question is about systematic and random uncertainties. So let's look at the nature of systematic uncertainties. A systematic uncertainty will result in all readings being either above or below the accepted value. This uncertainty cannot be eliminated by repeating readings and then averaging. Instead, systematic uncertainties can be reduced only by improving experimental techniques. A few examples of systematic uncertainties include the zero error. Another one is parallax error, a wrongly calibrated scale, and the reaction time of the experimenter. Now, where readings have to be made manually, it has to be accepted that there will be a delay between the experimenter observing an event and starting a stopwatch. This delay is referred to as the reaction time. The effects of reaction time may be reduced by starting and stopping the watch to the same stimulus, or making the time interval between starting and stopping the watch as large as possible. Now, in this question, you find that there is such an aspect of the reaction of the timer, and that is part B. In part B, they are saying that there is a constant delay between starting the timer and releasing the ball. Now, we have already agreed that this graph is supposed to be a straight line through the origin, like that. But you find that the straight line that is obtained practically does not pass through the origin. Now, what aspect of this graph shows that there is a constant delay? constant delay, that is a uniform delay. It's because this point ought to have been somewhere around here, below the actual line. This one will be above the actual line. Again, this one will be above the actual line. This one will be below the actual line. This one again below the actual line, and this one above the actual line. So you can see that the values which have been obtained actually in the practical are such that there is this timing here. Notice that the true value ought to be this one, but because of the delay in starting the timer, the actual value is this one. This is the amount of delay from this point all the way to this point. This is the amount of delay. Let's check the delay for this point here. You find that it is the same. The amount of delay is this much. For this point, the amount of delay again is this much. You see, the delay is constant. The delay is constant. That is why the actual graph does not pass through the origin. That's why B is the most likely answer for this section. There is a constant delay between starting the timer and releasing the ball. And you can see that for each point, there is that delay. There is that delay. Now, the reason why some points are above the line and some points are below shows the randomness of the measurement. That one is a random uncertainty, but it has not been mentioned here. If the random nature of the measurement was mentioned, then it would be true that the measurements taken have got that random uncertainty. But the fact that all of them are consistently greater than the true value by the same amount shows the systematic nature of this measurement. That's why B is the most likely answer.